let's begin. Modern EPCM engineering standards mandate an NPSH net positive suction head margin ratio, specifically NPSH available over NPSH required greater than 1.0. Explain why this specific margin is non-negotiable, and detail how this structural risk profile changes when transitioning from pure water services to hydrocarbon services.
The foundation of this mandate lies in correcting a widespread industry misconception known as the 3% head drop fallacy.
The 3% fallacy.
Correct. The standard NPSH required curve, or NPSHR, provided by a pump vendor, is not a safe operating baseline. It represents a mathematical state where the pump is already undergoing a 3% developed head drop due to cavitation.
Yes.
Therefore, an absolute positive NPSH available margin is required to suppress bubble formation and prevent mechanical damage before it even begins.
Let me stop you right there and clarify the physics of what you're saying, because this is a massive distinction. You are stating that the vendor's required suction pressure baseline is essentially a death sentence for continuous operation.
It is.
So when a manufacturer says their pump requires a certain inlet pressure, they are actively testing it to the point of failure.
That is exactly correct. During a manufacturer's shop test, they determine NPSHR by intentionally choking the suction pressure until the pump's developed head drops by exactly 3%.
At which point it's already failing.
Right. At that exact mathematical moment, significant cavitation is already occurring deep inside the impeller eye. The process fluid is vaporizing, bubbles are forming, and then as they move into higher pressure zones within the impeller, they violently collapse against the metal surfaces.
And explain how those collapsing microscopic bubbles translate into a macro-level mechanical failure.
Well, the collapse of a vapor bubble creates a localized microshockwave.
Oh.
When thousands of these bubbles collapse against the metal impeller asymmetrically, it causes severe material erosion, often pitting the metal like a sponge.
Pitting the metal.
Yes. Furthermore, these asymmetric shock waves introduce high-frequency vibration directly into the high-speed rotating shaft. This throws the entire rotating assembly out of balance.
What is compounding?
Exactly. Falling into the trap of using raw vendor NPSH3 data as a safe operating limit without adding the client-mandated margin leads directly to continuous cavitation, shattered bearings, and premature impeller failure.
So relying on the manufacturer's base curve is designing the pump to operate in a continuous state of self-destruction. If I'm signing off on a 20-year plant life cycle, I need a concrete buffer. Quantify this safety margin for me. What are the specific applications EPCM firms require?
For standard applications, the absolute margin is typically mandated as an absolute value, where NPSH available minus NPSH required is greater than or equal to 1.6 meters to 1.0 meters. Alternatively, it is expressed as a ratio where NPSA divided by NPSHR is 1.1 to 1.3.
Give me a field example.
For example, if we evaluate a pump with an NPSHR of 3.5 meters, strict EPCM standards will demand a minimum NPSHR of 4.5 meters in the field.
So a full meter of margin.
Yes. An NPSHR curve is a measure of performance failure. You implement a positive NPSH margin to prevent bubble formation and preserve impeller life. That is the fundamental rule.
That covers standard pure water. Let us move to the second part of the inquiry. Refineries move complex hydrocarbon mixtures. How does the physics of cavitation change when pumping hydrocarbons versus water?
It changes significantly due to the thermodynamic properties of the fluids, which introduces a hydrocarbon correction factor.
A correction factor.
Yes. Pure water flashes into vapor instantly when the pressure drops below its vapor pressure line. It is a violent, immediate phase change. Hydrocarbons, conversely, are multi-component mixtures of varying molecular weights. Because of this, they vaporize gradually over a temperature gradient.
I want to use an analogy to test my understanding of this mechanism. If water flashing to vapor is like dropping a lit match into gasoline instant, and explosive vaporizing a hydrocarbon mixture is more like boiling a thick, heavy stew. Different ingredients boil at different times.
That's a highly accurate analogy.
What is the mechanical implication of that gradual vaporization inside the pump casing?
The implication of that gradual stew vaporization is a thermodynamic cooling effect. As the lighter components in a hydrocarbon mixture begin to vaporize and form bubbles, they absorb latent heat from the surrounding unvaporized fluid.
They absorb the heat.
Right. This local heat absorption actually cools the immediate fluid slightly, which in turn drops the localized vapor pressure and suppresses any further bubble growth.
Interesting.
Because the cavitation is inherently less aggressive and self-limiting compared to pure water services, it allows for a mathematically lower structural risk. Under Hydraulic Institute Standard 9.6.1, an NPSH reduction factor can be applied to the pump design.
Here is my pushback as the EPC gatekeeper. If the physics explicitly show the risk is structurally lower with hydrocarbons, why do major EPCM specifications repeatedly mandate the higher water-based margins on hydrocarbon lines? From a procurement standpoint, are we not just over-engineering the systems, elevating massive suction vessels higher than necessary, and wasting millions in structural steel capital?
No, we are maintaining engineering accountability. While the theoretical physics allow for a reduction factor, major licensors and end users often choose to maintain the conservative water margin.
Why?
Because the cost of a catastrophic pump failure, a mechanical seal blowout, or a fire in a highly volatile hydrocarbon processing unit far outweighs the marginal capital saved by lowering a suction vessel by a fraction of a meter. We engineer for the absolute worst-case field operating scenarios, not just theoretical laboratory baselines.
I accept that logic for general processing. Does this conservative rule of thumb apply universally across all centrifugal pumps in the facility?
No, it does not. There is a massive exception to that rule that must be evaluated independently. High-energy pumps. When we deal with machines generating heads greater than 200 meters per single stage, the standard 1.1 to 1.3 margin ratios are completely insufficient.
Insufficient, even at those conservative ratios.
Yes. These specialized, high-velocity machines can experience highly destructive, localized cavitation, even when the NPSH available is 2 to 3 times higher than the required baseline.
2 to 3 times higher.
Exactly. For these applications, the margin cannot be a simple ratio rule of thumb. It must be rigorously evaluated based on the specific fluid's cavitation erosion characteristics and the impeller aerodynamic inlet geometry.
Understood. You have proven you know how to get the volatile fluid into the pump without vaporizing it. But surviving the inlet is only half the battle. Once the fluid is inside the casing, how we push it out dictates the mechanical health of the machine.
Correct.
Moving on to operational boundaries. How do you establish the preferred operating region, the POR versus the allowable operating region, the AOR boundaries, during a technical proposal audit?
The boundaries are dictated by API 610 standards combined with the physical limitations of the selected machine. API 610 section 6.1.12 clearly defines the preferred operating region, or POR, as extending from 70% to 120% of the pump's best efficiency point, the BEP.
Walk me through the actual fluid dynamics. What is physically occurring inside the casing that makes this specific 70 to 120% window the preferred region?
Well, within that specific volumetric window, the velocity and trajectory of the fluid flow perfectly match the physical angles of the impeller blades.
Okay.
Because the fluid is striking the blades at the intended aerodynamic angle, internal turbulence and flow separation are minimized. This aerodynamic harmony keeps vibration levels extremely low.
And the mechanical loads.
It ensures that the radial and axial mechanical loads thrusting against the bearings and mechanical seals are kept to an absolute minimum. It is the ideal, high-efficiency operating window.
To use another analogy, operating in the POR is like riding a bicycle in the absolute perfect gear on a flat road.
Yeah.
The pedal strokes match the mechanical resistance perfectly.
Ex-
So what defines the allowable operating region, the AOR?
If the POR is the perfect gear, the AOR is pedaling too fast downhill or grinding too hard uphill. The AOR represents much wider limits of operations set by the pump manufacturer.
Set by secondary constraints.
Right. The boundaries of the AOR are defined by secondary structural and hydraulic constraints. Unacceptable temperature rise within the casing, minimum continuous stable flow limits, motor power overload limits, and maximum acceptable vibration thresholds.
I'm going to challenge you on this distinction. If the manufacturer explicitly tests the machine and stamps allowable on their curve for that wider region, why are you overriding the people who built the machine?
Because treating the allowable operating region as a normal operating zone?
If I am a plant operator, I want maximum flexibility. Why artificially restrict the operational flexibility of the facility to the narrower POR? Defend that choice.
Because it exposes the EPC contractor and the end user to a severe long-term maintenance trap. Allowing a pump's normal daily operating process point to sit near the outer edges of the AOR exposes the machine to continuous high vibration and asymmetric hydraulic loads.
But the manufacturer says it's allowable.
While the manufacturer states the pump will not fail immediately in the AOR, running continuously in that zone will significantly shorten your maintenance intervals. Mechanical seals will degrade exponentially faster, and bearing life will be severely compromised.
provide a concrete engineering evaluation where you had to enforce this specific distinction during a project audit over a vendor's objection.
During a recent major proposal audit, a vendor selected a pump where the client's specified normal operating point sat at exactly 62% of the pump's best efficiency point.
62%.
Right. This was technically within the vendor's published allowable operating region, so the EPC contractor assumed it was acceptable and tried to push it through procurement. I rejected the pump selection entirely.
Explain the mechanism of your solution. How do you fix a 62% operating point if the plant's flow requirements cannot change?
You alter the machine to fit the process, not the process to fit the machine. As a rotating equipment engineer, you must plot all expected process operating points, minimum, normal, and rate it onto the vendor's performance curve.
And they must align.
The normal flow point must sit within the POR, and the minimum flow point must never drop below the AOR boundary. To fix the 62% issue, I requested a smaller, reprofiled impeller design from the vendor.
Modifying the impeller.
Yes. This artificially shifted the pump's best efficiency point to the left on the curve, thereby bringing the client's static normal operating point back perfectly into the 70 to 120% POR window.
Excellent.
The key line here is, keep the normal process point inside the POR to ensure low vibration, reserve the AOR strictly for short-term operational transitions.
And as with the suction conditions, I assume there is an exception to the 70 to 120% POR metric for highly specialized machines.
Precisely. When auditing high-speed or high-energy pumps, the POR can narrow significantly compared to standard API 610 guidelines.
Because of the forces involved.
Right. For heavily loaded machines, operating even slightly outside a specifically narrowed POR can trigger immediate flow separation within the impeller channels. This flow separation generates severe pressure pulses, essentially acoustic hammering, that can rapidly destroy mechanical components. You cannot blindly apply the standard rule to a high-energy machine without rigorously verifying the aerodynamic stability of the impeller design at those extremes.
Operating efficiently under normal conditions is expected. But refineries face anomalies. Process demands drop. Valves close. The system must protect itself. Next question regarding minimum flow protection.
Proceed.
You mentioned the minimum continuous stable flow, the MCSS, as a hard boundary. What are your strict engineering criteria for selecting an automatic recirculation valve, an ARV, over a continuous orifice bypass loop for pump minimum flow protection?
The selection criteria rely entirely on balancing upfront mechanical simplicity against long-term operational energy costs.
Let us define the physical arrangements.
A continuous orifice loop is exactly what it sounds like. It features a permanently open bypass piping line running directly from the pump discharge back to the suction vessel. It is fitted with a restricted orifice specifically sized to pass the pump's exact minimum continuous stable flow.
So it operates like leaving a faucet running all day, just in case you eventually need a glass of water.
Yeah.
What is the primary engineering advantage of this continuous loop?
Supreme reliability. There are no moving parts to fail, stick, or jam. It is mechanically simple and very cost-effective to install upfront.
And the drawback?
The critical drawback is that it continuously diverts flow away from the main refinery process. Because this bypass is permanently open, both the pump hydraulics and the electrical motor must be permanently oversized to account for the main process demand, plus the continuous bypass flow.
Wasting energy.
Exactly. This wastes a massive, continuous amount of electrical energy over the entire lifespan of the facility.
And the alternative technology, the automatic recirculation valve.
An ARV acts like a dynamic motion sensor faucet. It is a self-contained mechanical valve installed directly on the pump discharge nozzle. It features an internal spring-loaded check valve disc that modulates dynamically based purely on the main process flow rate.
So it adapts.
Yes. When process demand is high, the fluid velocity pushes the disc forward, which simultaneously closes the bypass port. 100% of the pump's energy is directed to the process.
And when demand drops?
When process demand drops dangerously close to the MCSF set point, the internal spring forces the disc back, opening the bypass port to ensure the pump always receives its minimum required flow to prevent destruction.
EPCM standards must draw a line on where to deploy which system. What are the hard selection rules?
EPCM standards generally specify continuous orifices for low horsepower utility pumps, typically those under 22 to 37 kilowatts.
Because the energy loss is minimal.
Right. The electrical energy wasted on a small 25 kilowatt water pump simply does not justify the high capital expense of an ARV. However, for large process pumps, high-pressure boiler feed pumps, or hot hydrocarbon export lines, an ARV, or a fully automated flow control valve loop, is specified to reduce operating costs and prevent continuous fluid heating.
I'm going to pressure test that thermodynamic logic.
Right.
ARVs are highly expensive pieces of specialized hardware. Suppose an EPC contractor attempts to cut project capital costs by specifying a simple continuous orifice bypass on a high-pressure, high-head pumping system. What is the explicit physical danger of approving that cost-saving measure?
Approving that measure introduces a highly dangerous thermodynamic trap.
A thermodynamic trap, explain.
Using a simple continuous orifice bypass on a high-pressure, high-head pump without performing a rigorous thermal analysis is engineering negligence. Here is how the physics unfold. When a pump generates massive high pressure, the motor imparts significant mechanical kinetic energy into the fluid. If that high-energy fluid is continuously recycled through a restricted orifice and dumped right back into the suction vessel, that kinetic energy experiences immense friction.
Immense friction.
It has nowhere to go. Therefore, the mechanical energy converts directly into thermal heat.
And because it is a closed loop, that heat simply compounds.
Exactly. Over time, this continuous fluid recycling will cause an excessive, dangerous temperature rise inside the suction vessel. It will eventually heat the fluid beyond its vapor pressure, vaporizing the liquid in the vessel and causing a total catastrophic loss of suction to the pump.
So it destroys the pump anyway.
Yes. Continuous orifices sacrifice operating efficiency for mechanical simplicity. You must specify dynamic ARVs for high-power process systems to save energy and prevent thermal leaks.
I have one final targeted counter-argument. You are portraying the mechanical ARV as the ultimate solution for high-power efficiency. As an auditor, I know that introducing complex moving parts introduces risk.
Of course.
Are you blindly trusting these mechanical ARVs in all high-power scenarios? Do they not introduce their own critical failure points?
I do not blindly trust any dynamic mechanical device, which is exactly why there is a strict field caveat to their use.
Which is?
ARVs contain internal moving parts, specifically the main spring-loaded disc and highly precise close-clearance internal guide channels. Because of these tight tolerances, they are highly vulnerable to sticking, galling, or jamming if the process fluid contains any particulate matter, pipe scale, or abrasive catalyst fines.
And if the ARV disc jams in the closed position while process demand drops, the bypass never opens. The pump runs completely deadheaded, boils the fluid inside the casing, and destroys itself in minutes.
Precisely. Therefore, for dirty fluid services or any process service with suspended solids, the engineering criteria strictly prohibit the use of mechanical ARVs.
What is the alternative then?
In those specific scenarios, I insist on removing the close clearance mechanical vulnerability from the primary flow path entirely. We replace the ARV with an external flow transmitter located downstream, tied to a logic solver, which operates a dedicated heavy-duty control valve on the bypass line.
Ah, external instrumentation.
It requires significantly more instrumentation and programming, but it ensures absolute reliability when the fluid itself cannot be trusted.
That concludes the technical audit. Your responses align precisely with the rigorous standards required for rotating equipment reliability.
Thank you.
And scene. Okay, dropping the cold, severe interviewer persona, adjusting my collar here, and returning to reality. Welcome back from the simulation, everyone, and to my co-host. Flawless performance in the hot seat. You really brought that grounded, hard-won engineering intuition to life.
Well, thank you. It is quite a shift from our usual conversational tone, you know? But diving into that deeply analytical mindset is exactly what rotating equipment engineering demands at that level. I mean, you can't casually debate with cavitation or thermodynamics.
No, you can't negotiate with physics.
Right. You just have to respect the physics and engineer around them.
Exactly. And connecting this back to you, the listener, whether you are an engineer actively navigating these dense EPCM standards, or just someone fascinated by how massive industrial infrastructure actually works, the main takeaway here is really profound.
It really is.
True engineering expertise isn't just opening a manufacturer's glossy catalog and taking their data curves at face value.
Right. It's about understanding the raw physical realities hiding behind those curves.
Exactly.
Knowing that the vendor's required suction line mathematically guarantees a 3% performance failure, or, recognizing that operating at the edge of an allowable region will slowly, methodically vibrate a multi-million-dollar machine to death over time.
It's about fiercely protecting the equipment's lifespan over short-term capital cost savings. The choice between a cheap continuous orifice and an expensive dynamic ARV isn't just an upfront line item on a procurement budget.
No, it's a 20-year commitment to either wasting or saving massive amounts of electrical power and protecting the facility from those catastrophic thermodynamic heat loops we talked about.
Yeah, it requires an ability to synthesize fluid thermodynamics, mechanical vibration profiles, and long-term economic impacts all at the exact same time.
It really does. It's a high-wire act.
It really is. But it leaves me with a final forward-looking question, something for you to mull over as we wrap up today's.
Listen, the days of flipping through static, outdated questionnaires, they are officially over. We're going to look at an entirely new ecosystem designed specifically for working professionals to help you master those high-pressure moments.
Okay, picture this. You're sitting right across the table from a panel of... They aren't asking about your hobbies anymore. They're dropping you directly into the hot seat to test your true operational readiness. Imagine you're in that interview. The pressure's on.
And that brings us to this absolutely game-changing app, which is available right now on the Play Store. What we're looking at here isn't just some random list of questions thrown together. No way. It is an exhaustively structured solution. It provides AI-driven, highly practical, example-based Q&As that form a comprehensive framework.
Because the sheer scale of this architecture is massive. We're talking about a structure spanning over 200 sections, and it caters to everyone, beginners, intermediate folks, all the way up to experienced and expert professionals. The rule of thumb here is simple. If it's in the plant, it is in this app. It really acts as a complete pedagogical roadmap for your entire career. Now, you might be wondering, how does it deliver all this content without getting super repetitive? Well, the core of this app is what they call the Studio Engine. It's this AI powerhouse that entirely eliminates the limitation of predetermined static questions. Instead, it dynamically generates a highly structured, unlimited repository of practical Q&As right when you need them. So by doing this, it actually tailors a dynamic mock interview simulator specifically to your current knowledge gaps. It brilliantly illustrates how concepts are queued sequentially. You just select your domain, your section, and then your concept, and the app continuously feeds you the next logical scenario. Because getting a question is one thing. Understanding the multidimensional answer is a whole other ballgame. The system doesn't just feed you a wall of text. Every single generated response is deconstructed into 5 distinct steps. It actively highlights the critical responses you absolutely must deliver and warns you of the hidden pitfalls. Now, they represent only a minor part of the unlimited Q&As available in the app, but they serve a very specific, crucial purpose. They perfectly simulate real-world office arguments, differing viewpoints, and intense technical debates. Because let's face it, engineering isn't just taking a test in a vacuum, right? It's about navigating heated arguments and proving your technical acumen when challenged by your peers or your superiors.
And a massive part of these sessions is the power of roleplay. After every mock interview section, videos feature AI-generated live roleplay interview sessions complete with feedback on pertinent domain subjects. Giving real roleplay interviews after enriched technical discussions acts like an incredible catalyst. It is a tremendous confidence booster for any aspiring candidate, consolidating everything you've learned into practical, real-world readiness. Which leaves us with one final, very important thought. What step are you going to take right now to engineer your own success? Mastering your craft is a lifelong pursuit, and with tools like this at your fingertips, the depth of your knowledge truly has no limits. I highly encourage you to check out this combined integration of texts, text-to-speech audio, videos, and live role-play interview sessions. The tools are definitely out there to unlock your potential. The only question is, are you ready to use them?